Alright, now limits were good. Limits are the beginning of calculus. Limits are essential to understanding calculus. But now we're getting into the really good stuff, the fun of what we're going to do this semester, which is the derivative. Don't even get me started on the antiderivative, and actually don't, because you'll do that next year. So we're only going to do derivatives this year. But anyway, that's what we're going to start now. So we need to really understand what a derivative is and what it represents. Spoiler alert, derivative is the slope of a tangent line. Another way to think of that is it is a rate of change. It's crucial that you understand those pieces of information, and I will emphasize that multiple times. So what we're going to look at right now is understanding how we get a derivative, how we find the derivative from finding the slope of a tangent line, and then, as I just said, understanding what a derivative is. So first we need to talk about a tangent line. So a tangent line is a line that is tangent to a curve. So a line is tangent to a curve at a point P if the line is perpendicular to the radial line at point P. So what does that mean? Well, it's really easy to see that with a circle. And you did talk about tangent lines in geometry, so this isn't new. But so if this is the radius of a circle, then this line would be tangent to that circle. And as I move around the circle, the tangent line is going to change. But what we're going to look at is how to find the slope of that tangent line. One thing we want to note is that although a tangent line doesn't intersect a circle, they may cross through a point on a curve depending on the curve. So what I mean by that is, for instance, if I draw, like, let's say, this curve like this, well, remember when we say a tangent line, it touches it creates the point of tangency where it's perpendicular to the radial line at that point. So it doesn't intersect the curve at that point. However, what this is saying is it could intersect the curve somewhere else. So for instance, if I have some point of tangency here, then my tangent line would look something like this. So it does not intersect the curve at the point of tangency, but it could intersect the curve somewhere else. That's just something we want to make sure we understand about a tangent line. It's not crucially important, but it's basically understanding that when we say tangent line, that doesn't mean that it never intersects the curve. It just means it doesn't intersect at the point of tangency. Okay, beating that one to death. All right, moving on. So the tangent line problem. We saw this the very first day of limits when we did this in class. So I'm going to go through this a little bit quicker this time, but it's the same idea. So I have my picture here, you have the same picture. I have this point Q, which is the coordinates x2, y2. I have this point P, which is the coordinates x1, y1. The difference between x2 and x1 is delta x. The difference between y2 and y1 is delta y. So first, let's talk about finding the slope of the secant line. Well, I know the slope of the secant line is y2 minus y1 over x2 minus x1. And so now I need to do a few substitutions. So I'm going to point out a couple of relationships. Well, I know that x2 minus x1 is actually delta x. I know that y1 is actually f of x1, and I know that y2 is actually f of x2. So those are all just, substitutions, other notations for the same thing. But now, in order to create what we want, because that's what we're doing here, I'm also going to say, okay, but f of x2, or y2, is the same thing as f of x1 plus delta x. And I'm getting that by, if I look at this equation right here, well, we could say that x2 is x1 plus delta x by just rearranging this equation. Okay, so now let's do our substitution. So I'm going to substitute into my slope of the secant line, and I'm going to say now m secant is, instead of y2, I'm going to say f of x1 plus delta x, and instead of y1, I'm going to say f of x1 over, and instead of x2 minus x1, I'm just going to say delta x. Boom, created the difference quotient, right? That was awesome. Okay, but we don't care about the slope of a secant line. What's the whole point of this? This point is the slope of a tangent line, right? Well, how do I find the slope of the tangent line? I use a limit. So the slope of the tangent line is going to be the limit as delta x goes to 0 of f of x1 plus delta x minus f of x1 over delta x. Because what is this saying? It's saying as the change in x, so as the x's get really, really close together, these 2 points are going to get really, really close together, eventually becoming the same point, and therefore creating the slope of the tangent line, or the tangent line itself. So that is our tangent line problem, is understanding that the slope of the tangent line is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. This is our limit definition of a derivative, because the derivative represents the slope of the tangent line. So, the derivative of a function. Differentiation is the limit process used to define the slope of a tangent line. That's what we just talked about. Of course, this is a major point of calculus, and we will differentiate until the cows come home. Assuming the cows come home, although I'm guessing most of us don't have cows, so that could be awkward. But, moving on, the definition of a derivative, provided the limit exists, is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. How did we get this? Well, really, it's just a fancy slope formula, right? That's what we did. We did y2 minus y1 over x2 minus x1. The only difference is we're doing it as the change in x gets infinitely close to 0, and then it becomes a tangent line. So again, it equals the slope of the line tangent to the graph of f at some point x comma f of x. This is one of the notations for a derivative. We're going to see more notations for a derivative in the next video. Okay, so we need to understand differentiation is the process of finding the derivative of a function. Good. So this is a vocab thing. You're going to need to understand that. The limit definition of a derivative is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. That is our difference quotient. It is very important that we understand it represents a derivative when the limit is involved. If the limit's not there, then it's not a derivative, it's just a difference quotient. But as soon as we put that limit in, and specifically this limit, that as the denominator goes to 0, keep in mind also, remember this doesn't have to be delta x. Whatever it is though, this, and this need to be the same. So for instance, first semester we saw these as h's. It could be any other letter you want. It could be your name, whatever you want it to be, but it has to be the same thing. That's when it becomes the limit definition. And again, as I mentioned at the very beginning, the derivative represents the slope of a tangent line to a function. Incredibly important that you understand that. If you don't understand that, derivatives are just going to be really confusing when we talk about applications. And again, another way to say slope, and this should make sense, hopefully, is rate of change. That's another key phrase you are going to hear over and over and need to understand. That's just saying derivative. All right, good talk.